It's a great pleasure to have Emtiyaz Khan, also known as MT, to give another edition of the EPFL CIS and RIKEN AIP talks. MT is currently a team leader at the RIKEN Center for AIP in Tokyo, where he leads the approximate Bayesian inference team. He's also an external professor at the Okinawa Institute of Science and Technology. And he was a postdoc at EPFL as well as a scientist, where he taught two large-scale machine learning courses. He created also a nice email list, ML groups at EPFL that is currently, I don't know, maybe have more than 500 people or something like this. Now, he finished also his PhD in machine learning at UBC, but okay, he also got a teaching award at EPFL, which is really prestigious. And today he's going to talk about more about Bayesian learning rules. And with that, please take it away, MT.
Thanks a lot for the very nice introduction. It's really nice for me to come back and give this talk about my work since I left EPFL in 2016. So I thought that I will start with some joint things that have actually happened due to my association with EPFL. Since I moved here, many people have actually come and visited and spent some time with us in our group. And here's a list of 6 students. And thanks a lot to Patricia, Janet, and Sylvian, who have been actually helping us all these years and sending me a postcard every year. I get a New Year's card from them. So yeah, these students have actually done a lot. They've written quite a lot of papers with us, and it's pretty amazing that master's level students can actually write, in top machine learning conferences. I've shown some of their work in red. Some of them have written theses, others have written papers. And also some of you who have actually, some of you at EPFL have taken the course now. I think now Martin, Yagi, and maybe Nicola Flammarion is also teaching it this year. And I went back and I tried to sort of look into how the lecture notes are going. And I'm very happy that they're still kind of using some of the things that I actually did back in 2014. It was a large course at the time, and now it's become even larger, I've heard. So these are some of the connections to EPFL. But maybe now I start with what I've been actually doing in the last a few years since I've left. And start with the big picture. The goal of my research and my group's research is about designing AI systems that learn as quickly as humans and animals. So we want these artificial intelligence systems to quickly adapt to new situations that arise in the future, but robustly preserve the past knowledge and then use it to learn the next set of things that are coming in their way. And if you've seen my course before, I've seen my talk, I showed this video of my daughter where she's trying to kind of learn by adapting to her environment. And in the beginning, she's trying to figure out what kind of experiences she likes in the world. And she's slowly figuring out that the sound that comes from the fretboard is the interesting thing for her. And if you give her enough time, so at 1 year age, so after 6 months, she's kind of figured it out. Her algorithm in her brain has somehow converged. So she knows what she wants. She wants the sound that comes from the board, and she's trying to relive that experience again and again. Now, if given more time to her, she uses her past experiences to kind of transfer it to novel, situations. So here from ukulele space, we have gone to a guitar space, which is a slightly bigger instrument, but she's somehow getting the same experience that she was getting before in a very new, novel way. So this kind of quick adaptation is pretty amazing in machines, in humans, but in machines, this is not yet there yet. Machines have difficult time in quickly adapting to the scenarios, but sometimes they can fail because maybe they trusted the new data, the new things that were coming their way too much. So this is an example of Tay Tweets. This was a chatbot that was put in place by Microsoft. So it was put in place in the morning, and it was supposed to learn from other people's tweets and adapt to it over the coming days, but just within 24 hours, it learned to say many bad things, like many racist things. So this system was clearly, it was forgetting the old knowledge that was given to it during training time, and it's adapting too quickly. But there are also kind of the other way cases where the machines are too slow to adapt because they're very rigid. And this happens in this kind of robotics application where the system is too rigid. And if you move slightly some things in the environment, the system is unable to cope with this small insignificant change and then fails. So my question has been is that how can we design this kind of adaptive yet robust learning systems? And I'm vouching for some algorithms that have this kind of Bayesian side to it. So my goal in this talk is to argue that the good algorithms that can balance robustness and adaptivity, like what my daughter was doing, that kind of algorithms have a Bayesian side to them. So whether they're Bayesian or non-Bayesian, we can always see them as approximating some kind of Bayesian posterior. So I will try to make this point in this talk. I start by looking into a new algorithm that I call Bayesian learning rule, where by approximating the posterior distribution using some appropriate posterior approximation, we are able to unify and generalize many existing algorithms that are found to work well in practice. So then we'll kind of take this Bayesian learning rule, we'll build up on it, and then we'll try to show that if you want to preserve some old knowledge that has been gathered through this kind of learning rule, then you can define these kind of concepts like memorable experiences of your past knowledge that helps us to incorporate robustness in the system. And then I'll show finally how this memorable experiences, then they can be used to do adaptation through some kind of prior. So you will take a prior where you do some comparison between your past experiences and new experiences, and that'll help us to trade off make this trade-off between robustness and adaptation. The key takeaway of this talk is that there is a modern perspective base that I'm going to talk about that I believe is essential for this kind of robust and adaptive learning to design AI systems based on machine learning, deep learning. This kind of Bayesian perspective is essential. And some of these works are already out. So here are 5 papers I have listed here. So I encourage you to check those out. The ones that are out already. Okay, so let me start with the big picture. So there's this big question of what makes an algorithm good, and what are some of the common origins of good learning algorithms. So I draw an analogy here to the origin of species and natural selection, because the question is kind of very similar. So origin of species is about natural algorithm. And here we are talking about artificial algorithms, right? So it is clear that that good algorithms, whether they're natural or artificial, they must sort of revise their past belief by using, by extracting some useful information from the new data that's coming in. And this should also be true of the algorithms that are derived through like empirical experimentation and intuition and hacks. For example, many of those are used in deep learning. We don't know why they work, but we expect that these algorithms also have this property that they're revising their past belief using some of the new data that's coming in. So we're kind of arguing that it's possible that all of these good algorithms, they have a common origin. that they optimize similar objective, and they use similar strategies on how the optimization proceeds. Then the question is, what is that common objective? What is that common algorithm? So in this paper that we wrote recently, we are arguing for a Bayesian origin, and we propose an algorithm called Bayesian learning rule. Essentially, so there's this table in the paper where we show this first column is the different kinds of algorithms, and they're from like optimization, they're from deep learning, so methods like SGD, RMSProp, or Adam, dropout, and other things, and some algorithms in approximate inference literature like Laplace's method, EM algorithm, and there's some message passing algorithms, basically saying that all of these algorithms can be derived from this single rule, where we'll have to make two choices. We have to change the approximation to the posterior, so we can choose a different form, and that's this column here. And then once we've chosen the approximation, we need to make some approximation to the gradient, and we're using a special kind of gradient in this learning rule, which is a natural gradient. We're going to do some approximation to this to get these different kind of variants. Okay, so that's the kind of the thing that I'm going to talk about for next 10 minutes or so. Okay, so getting into the details a little bit. So when I said the objective that these algorithms are optimizing, we are arguing that they are kind of Bayesian origin. So they look something like what's shown on the right-hand side. So they're different than what people usually use in the non-Bayesian world. So you're minimizing a loss function with respect to theta. Maybe it's a regularized loss function. So something like a maximum likelihood principle or empirical risk minimization. It looks like something that is in the left-hand side. We are arguing that we should be aiming for something that is in the right-hand side. What we have in the right-hand side is that we are regularizing the problem using a distribution and its entropy. So Q is a distribution and it's a posterior approximation. We're going to assume it to be exponential family throughout the talk, but it's some kind of approximation to the base posterior. And now instead of minimizing the loss, we are minimizing the expected loss under this distribution. So we're basically saying that if we sample from this Q of theta, different models, all of those models should give us lower loss, but they should also be sort of diverse. So they should be somehow regularizing the entropy. So they should be far from each other. And this is inherently a Bayesian principle. This is very old work by E.T. Jaynes from 1957 that connects it to Gibbs distribution, Gibbs free energy, Gibbs measure. There are many names to this. And many other people have actually given talks in this series. So it's kind of connected to all of this other work, even though I'm using the word Bayesian here. Okay, so this is the first point, that you would optimize something like what's written in the right. You will use a posterior approximation, something like exponential family, one. And the second point is that we'll use a special type of algorithm that we'll call Bayesian learning rule. It's actually a natural gradient descent algorithm on this objective. Okay, so we're going to do natural gradient descent, but there is a very specific parameterization that's being used. So we're going to update the natural parameter of the exponential family, and we're going to take the gradient with respect to the expectation parameter. So if you actually don't remember what exactly natural and expectation parameters are, don't worry about it. Just think of them as different functions of like mean and covariance of a Gaussian. And we'll see the exact form of what those functions are, but they're just two different kind of parameterization. They're actually dual of each other in a sense. So you're using this kind of dual coordinates to update your parameters. So what's actually happening is that old belief is somehow encoded in the natural parameter of the distribution, and new information, the innovation, is coming in through natural gradient. So natural gradients, the information geometry of the problem, is telling us the new information that needs to be added to the old belief. So this is the construction. And what we can now show is that if you use this posterior, So by using posterior's information geometry, we are able to balance new and old information. And what we are then showing is that when you change the form of the posterior, so Q of theta, so that's the first step, the second column here, then so you'll choose different forms and you'll get different methods. Then you'll have to do some approximation, okay? So just to make this a little bit more concrete, I'll go through the simplest possible algorithm, gradient descent. So I hope most of you know what gradient descent is. So you're just updating the parameter using the gradient of the loss with a step size. And the claim here is that if you choose a Gaussian with a fixed covariance, so covariance could be anything, it could be arbitrary, but I've chosen it to be identity 1 here. But with that choice, I have shown some what the natural and expectation parameters look like. I hope that it actually makes a little bit of sense that there's only 1 degree of freedom in this distribution, just the mean. The covariance is fixed. So the natural parameter and the expectation parameter, they're both m. And the entropy of a Gaussian with a fixed covariance is constant. So it's very easy. Now we take the Bayesian learning rule. Well, it's natural gradient descent on the Bayesian objective. And because the entropy is constant, it sort of goes away. And what I've done, now I've just plugged in the definition of natural parameter, which is the mean, expectation parameter, also the mean. In this case, it turns out to be very, very simple. So you can see already that this rule is looking very much like that rule. But now the only difference that we have is that the natural gradient that we're computing here is actually exploiting the expectation. It's exploiting the geometry of the distribution. And so it's kind of a Bayesian version of the gradient descent. And if you don't want the Bayesian thing to happen, perhaps you could just choose 1 point. So you could choose it to be the mean. And this is a very classical approximation that's known. So this is the natural gradient approximation that we are doing in this case. So we're just approximating the expectation at the mean. It's a very greedy approximation. If you do that, then you recover the gradient descent. Okay. So what I show you is that if you choose a Gaussian with a fixed covariance and you approximate your natural gradients at 1 point and ignore the expectation, then you recover the gradient descent. Now, this is a point that many people don't like, this delta approximation, and neither do I like it. So, what actually this whole thing has been about is that once you see gradient descent as an approximation of a Bayesian scheme, now you can, try to improve the algorithm by injecting some of the Bayesian-ness into it. So you can try to put back the expectation in. So that has been sort of my work that I've been doing for some years to show why this principle is actually useful to see gradient descent derived from a Bayesian origin. So I want to convince you a little bit in the rest, maybe next 10 minutes or so, is why we should be having this kind of expectation here actually helps. So maybe let's first look at the simple visualization of what this expectation actually does. So consider a loss function. Suppose the loss is kind of this multi-modal loss. So you have many local minima in this case. What you can see when you take the expectation, for example, let's say your candidate distribution Q of theta is the Gaussian. When you take the expectation, you get a loss that's now, because theta is averaged out, loss is a function of the mean and the variance. So it's kind of this plot that I've done here. It's a 2D plot with the mean in the x-axis and the standard deviation on the y-axis. You can gain a little bit more understanding of what happens with the expectation when the variance is changed. So if you increase the variance, you could see that the loss with respect to the mean is kind of a smooth loss. The expectation can be seen as some kind of smoothing, some kind of perturbation, or some kind of Gaussian convolution in this case, right? So what the Bayesian objective is actually saying is that instead of optimizing the original loss, which has many local minima, maybe they're spurious, they're not important, we should be doing an expectation that makes some of them go away. So it gives us some kind of stability to your loss by choosing this kind of perturbation. Now, this idea has been lately becoming very popular in deep learning. So this comes under implicit regularization of SGD, that SGD is actually doing some kind of smoothing, some kind of noise injection, some kind of perturbation. And that's why it's actually working well. And this kind of connects to this kind of Bayesian principle. There have been papers written on it, like entropy SGD kind of method. And also some people have given talks in this series about SGLD, so like longitudinal style methods. They're all kind of sort of doing this kind of perturbation. And this perturbation helps us to avoid some of the local minima and go towards more dominant minimum. This is also common in reinforcement learning, search, and robust optimization. So like methods like continuation methods, optimization by perturbation, there's a huge literature on this topic. What is important here and why we call this Bayesian is because the kernel that smooths the, so like the variance in this case, smooths the loss, it's also automatically being learned. The rule has the flexibility to be able to learn how much should you smooth according to some kind of uncertainty, right? So it's actually quite powerful. And I believe that we are yet to see what all is possible with this framework. So I hope that this puts some things in perspective, that the Bayesian principle doesn't look very different from other things in the non-Bayesian world that many of you may know. But let me go a step further and try to maybe argue why Bayes' objective is doing something more like what stochastic gradient descent does, and it's different from gradient descent. So there's some kind of flatness in the solutions that you find. So let's take this gradient descent algorithm, and you know that the fixed point of this is that when you take the gradient at one point, it goes to 0. That's the solution of this gradient descent. With Bayesian learning rule, if you put the expectation back in, it suggests to use this update instead. So you should take the gradient of the expectation, and the mean is actually sitting in the distribution, right? So if you look at the fixed point of this, essentially you get this gradient of the expectation equal to 0. So it's slightly different. It's the gradient of the convoluted loss that's being set to 0. Now, what we can argue is that the solution, the Bayesian solution that you see at the bottom here, it has this kind of property that is trying to inject some noise through the distribution Q, right? And this noise has some kind of similar regularization effect as implicit regularization of SGD. So for example, if you take this kind of loss function, this is like logistic regression, has this kind of loss where it's unsymmetric around the minimum. So this is the minimum. The loss is really flat on one direction. On this side, it's very flat, and it's really high. It's a wall on the other side, right? And if you actually run the stochastic gradient descent on this, and I'll show this soon, it will actually push you towards the flatter direction. The Bayesian solution has a similar property. So when you do convolution, you do smoothing, some of this high, large loss spills inside, and it pushes the solution to the other side, okay? So as you increase the variance, more and more high loss will spill, and your loss, your minimum will push towards the flatter direction. Okay. To make this a little bit more clear, you could actually, so you could rewrite this gradient. So what I've done here, I've used a theorem that's called Bonus theorem. It's actually very simple to prove. Essentially what it does is that you could show that this gradient is exactly equal. This gradient of the expectation is equal to the expectation of the gradient. So here the gradient is taken with respect to the mean. You can then push it to make it gradient with respect to the parameter theta. And here you see that the fixed point of the Bayesian objective is not like the gradient should be 0 at one point, but rather you want the gradient to somehow cancel out. So the gradient from the high loss region, gradient from the low loss region, they need to somehow cancel out. So the distribution has to shift slightly away to that side for that to happen. There is an explanation of this in the paper, and I encourage you to look into figure 1 of the paper, and it's explained there. just to show on empirical, so this is all kind of drawings, but you can actually show this on a real problem. So this is logistic regression, one-dimensional, very, very simple one. And the minimum is here, and this is like really flat direction. So you can't see, but it slightly goes up and goes in that direction. And if I run SGD on this with a very, very small step size, the iterates actually are very, very close to the star. But if I increase the step size, what happens is the noise that comes from the high loss, it tries to push it to the other side. So if I keep increasing the step size, my iterates actually gets pushed away quite a lot because of this stochastic noise. They go towards that direction. Now, if you do the Bayesian learning rule, where you fix the variance, so I fixed the variance to 1 in this case, it has the similar property. So the solution will move towards this side because it's trying to avoid this high loss region, which is on the left side. And it's really because of this equation. Your gradients have to balance out, and so it has to be sort of away from the minimum. So by increasing the variance, now you can move the mode arbitrarily far. And so this kind of Bayesian noise, it has a similar regularization effect. And of course, this is on a very slow example. We don't have theory yet, but I hope that people will work on this and see this connection and make use of this to show that there are similar Bayesian principles behind working of these kind of stochastic algorithms. Okay, sorry, I'm going to take the questions later. So I see that there are some things coming in, but I'll try to, or should I take the questions now?
Actually, no, I think the audience should input the questions in Q&A, and it's up to MT to decide if he wants to answer now or at the end. Typically, we take it at the end, but MT is the boss.
Okay, well, there's a question I will actually say, I will do it. So in page 13, if loss function in Bayesian learning rule is same as the standard loss, the second term might be KL between the prior and posterior. I'm wondering if we use entropy in the second term, and the first term might be joint distribution. This is different with the standard loss function. Do you have any comments on this? Yeah, this is a good question. And sorry, I didn't have time to explain this, but going back to this slide, you're right. So I've actually assumed that this is a regularized loss. So there's a regularizer inside it. So if you actually pull the regularizer and write the log probability of the regularizer, then you can write this entropy as KL. So it will become relative entropy. In case there is no regularizer, then in that case, it's not really kind of Bayesian, but it's pseudo-Bayesian. So sometimes people use the generalized Bayesian framework, and then it will be related to the Gibbs free energy. So if you have a prior distribution or a regularizer, then it may correspond to the Bayesian model, but in general, it could be just a Bayesian principle, which is run on an a loss that's not a probability. So actually, the original paper of E.T. Jens was kind of open about these things. So he was not really thinking about Bayesian models at the time, but it could be arbitrary loss. So thanks a lot for asking that question. Let's now go to the second part. So far, I've only shown you a very simple algorithm. So I've shown stochastic gradient descent, gradient descent. And now I will try to show another property of Bayesian learning rule that is quite striking. So it turns out that there is a one-to-one correspondence between the complexity of the posterior approximation and the complexity of the learning algorithm. So if you increase the richness of the sufficient statistics of the posterior approximation, the types of information that the algorithm is learning, it increases. To make this a little bit concrete, let's say that this is our posterior, and we choose a very simple approximation like we chose for gradient descent. So only the mean can change and the covariance is fixed. In that case, we will get gradient descent out of it. So I just showed this to you. But in case we increase the complexity of the posterior approximation, so we make it more rich. So now let's say the covariance is also allowed to vary. And if you do the same calculations, and I'll show this very soon in the next slide, until you plug this in Bayesian learning rule, you'll get Newton's method out of it. So you'll get a second order method. If you increase the complexity of the posterior approximation to make it mixture of Gaussian, so you have many components, and you plug that in, the Bayesian learning rule, it becomes a multimodal optimization algorithm. So it's like a mixture of Newton, where you're running many chains of Newton method, and they're all kind of pushed away from each other due to the entropy. So there's some kind of responsibility they have to share of different regions in the landscape. So it comes out very, very naturally, and it's very powerful. So it's, if you keep on increasing the complexity to the posterior, the exact posterior, then you'll get Bayes' rule out of it. Okay, now, so how does this kind of work? I'm not going to go through the detail of this, but it's actually there in the paper. So you can see section 1.3.2 in the paper. The mechanism is very, very straightforward. You start with the algorithm, you write down the posterior, these details. So like net parameter, expectation parameter, you plug it in, you do some calculation, you simplify, simplify, simplify. These are all exact, by the way. There's no approximation here. You just kind of try to write it in a form such that the Hessian and the derivative will show up. Okay, so stop here, because you start to see actually that this algorithm is looking more and more like this. There's a preconditioner here. Preconditioner is learned through the Hessian. If you do a little bit of step size selection, if you set the step size to 1, you'll get the Newton's method. But what we actually, so this is the derivation of the Newton's method. You see that the second derivative sort of comes when you increase the complexity to let the covariance matrix also be flexible. What is astonishing here is that this update, actually, if you see here, there's a moving average style thing. So it's actually saying that you should, the preconditioner should not just be Hessian, but it should be Hessian plus convex combination of the Hessian and the past preconditioner. And actually this, if you look into this a little bit more, turns out that it's actually very, very similar to RMS prop. So these kind of optimizers that are being used in stochastic settings, this the form of this scale that is obtained through 1 minus rho and rho kind of convex combination, this automatically pops out due to this Bayesian principle. So actually this term comes because of the entropy. So it's very fundamental why we see this here. So it was a very nice surprise for us to see that RMS prop-like algorithms are similar to what the Bayesian principle would suggest through this Bayesian learning rule. And then that helped us to design new deep learning algorithms where we can kind of put the expectation back in. So we are now injecting the noise by sampling this data. So this algorithm is essentially what I showed you in the previous slide. So this algorithm is basically being implemented in this pseudocode, where we make some approximation to the Hessian, because in deep learning it's hard to compute Hessian. So we do some kind of Gauss-Newton approximation, but it's not completely necessary. There are other variants now we have where we don't have to do that. But the nice thing is that the code of this new Bayesian algorithm is very, very similar to what we have in RMS prop. So only these red parts are different. So we now inject the noise. And we show that this S that we get here, the scale in the deep learning algorithm that adjusts the gradient, now that scale essentially gives us the variance. So this was then the proposal to do Bayesian deep learning to estimate uncertainty from RMS prop and Adam-like algorithms, so modifying just few lines of code, putting the expectation back in to improve some of this kind of smoothing effects, to understand, to get a better estimate of the uncertainty. And this works quite well, actually. So here I've just shown this for a toy example on the left-hand side. So Adam is just giving you one estimate, so one classifier, while Wogan gives you the mean and the variance, which you can use to sample. So there are many samples here that you get. So it kind of tells you whether the data is not there. So there are many other models that can minimize the loss. Then they're kind of diverse because of the use of the entropy now. So it's very nice extension that came out which surprisingly, so this was the first time when this paper was written in 2019, that we're able to get Adam-like performance using the Bayesian method. So we have almost the same kind of convergence behavior. And because the algorithms are similar, like Adam is similar to this Bayesian learning rule, we're able to kind of borrow all the tricks from deep learning and then put it in the Bayesian flavor in there. And that kind of helps it to make it very similar to Adam, but then calculate the uncertainty, a good estimate of uncertainty that Adam is not able to do. So we've been kind of working on this, and now so we have a couple of papers. So this is the 3 papers over the years. And this last year at NeurIPS, some of our group members and somebody from Munich, we teamed up, and then we applied this to this challenge for approximate inference. And we didn't really try very hard, but we still got first prize in the 3 categories there. And we were sort of using this kind of this Bayesian learning rule, the one that I showed in the previous slide, but we used a slightly improved version, which makes the implementation even easier. It's very, very similar to Adam. And we use some kind of ensemble using this mixture of Gaussian type of idea. So all of these ideas that derive from Bayesian principle, they work quite well in practice, and we were very happy with it. So I hope that this sort of encourages you to look more into it and not get just scared because it's Bayesian, so it's very different. But the world's kind of very similar if you use this viewpoint to see. There are other things. So see the figure 1, there's like, you can show now that the flatness is still kind of happens when you're able to adjust the variance. So you can kind of go to different kind of flatter solution now. So it has this kind of property. You can apply it to this kind of video thing. This is actually done by Roman, who is in EPFL now. He's a PhD student, I think. Yeah, if you're interested in these things, I gave a long tutorial at NeurIPS about this. So please check it out. Okay, so I've used about 40 minutes now, and I was thinking I'll take the next 10 minutes to talk about robustness and adaptation. Is that okay, Vulcan?
Yeah.
Okay, great. But maybe I could look into it. So there's some questions that are coming. Okay, so there is a question by Manish. How can we quantify the prior in such cases? Yes, so quantification of prior is a thing that one should worry about. But really, you could see that deep learning people use a very mild regularization, and there is also regularization that's put in through this kind of implicit algorithmic regularization or dropout or something. All of those things can now be used in this Bayesian principle as well. So it's not a proper Bayesian model, but you can still kind of obtain uncertainties that are similar to those that will be given by a proper Bayesian model. So I'm not saying that this is solving that problem, but this is kind of orthogonal to the things that I'm showing here. There's another question: can we recover all optimization algorithms using Bayesian principle? It's a great question. Many times people ask this question. And really, like here, I'm not making that claim that all algorithms are Bayesian. I'm simply saying that there's a viewpoint that helps us to connect the good algorithms and then use their strength and borrow their strengths. So it's a hypothesis that's way too far. I would not go into it to say that all algorithms are Bayesian, but some of the good properties of algorithms, like the ones that I'm talking in this, to balance the new and the old information, those properties we expect them to have a Bayesian-like flavor, is what I'm actually saying. Okay, so thanks a lot for the questions. Let's then, sorry, I'm only reading the ones in Q&A and not looking at the chat because I'm scared there are 5 messages there, but I'll get to it maybe in the end. Okay, all right, so then let's go into this adaptation and robustness. How can we use this Bayesian learning rule to get into to design AI systems that are adaptive? Now, one thing that what I'm kind of the point that I'm trying to make through all of this kind of principle, Bayesian principle stuff, is that good algorithms, they're expected to appropriately balance new and old information, right? So we expect them to also being able to tell apart what information is relevant to them and what is irrelevant, right? So if some new information being thrown at the algorithm and it's stable and it's robust, then it's able to reject those new information and the minimum doesn't change, right? So somehow good algorithms, the solutions that they will find, we expect them to be insensitive to irrelevant information, whatever that is, while be very sensitive to new information that they should account for and move accordingly, right? And somehow we should be able to get this from the solution. So we should be able to look back into what information, the old data that was used to train the algorithm, what information in that data was relevant, what was irrelevant. So it's like what my daughter was doing. She's recognizing that the music is good for her and everything else is bad. So can we dig this out of an algorithm is the question. And I've been actually studying this question for the past 3 years or so. And a central concept that comes always back to this is that, well, if you want to understand what is relevant and irrelevant, what is important and unimportant, then we could probably understand this by perturbing the parts of the model. So we can kind of hold some parts constant and see how the output changes. And if the knowledge is sort of forgotten, then maybe that part is important. And if the important knowledge is not changed, then maybe that part is not important, right? So this is the whole idea of perturbation to sensitivity, and then duality. So duality kind of tells us how sensitive the global solution is to the local perturbation. That's very common in optimization, as some of you may know. So what we are actually now showing in our new works is that if you look at the Bayesian learning rule solutions, you can actually read off the duality from the solution directly. You don't need to do any other additional effort. So this is kind of the key point. Just to give you a sense of how this comes out, think of like your loss function as being built by several data examples. So maybe there are n data examples, and maybe they're not all equally important, right? So you have n data example, and then you have a regularizer. So it starts with 0. So you have n+1 terms here. If you apply Bayesian learning rule, then you'll get n+1 terms for the natural gradient, which is here. Then actually, if you look at the fixed point, the solution that it finds, it's essentially kind of lambda being set to equal to this natural gradient. Then you can see that this global parameter is made up of these smaller natural gradients, right? So you add many natural gradients for each data example, each term in your loss, and somehow the ones that are for which the natural gradient is bigger, they are actually contributing more to lambda star. So it makes kind of sense that natural gradient will tell you which example is more important than the other, right? So this is in the intuition. And I'm writing this as lambda tilde here to say the local is tilde. It's a local natural parameter that's being summed to get the global natural parameter. But this doesn't stop here. So what is really, really amazing is that it turns out that these natural gradients that we find, they're also some kind of Lagrange multipliers, meaning that they're measuring the sensitivity of the solution, so this lambda star, to local perturbations in this natural gradient. There's a specific form of the perturbation, and this is kind of written in this paper, so I encourage you to read that. But you do perturbation in the moments, and it corresponds to the perturbation in the moments, these Lagrange multipliers. So these lambda tildes are actually telling you the sensitivity of the optimal solution. So actually, many years ago, I was talking about this to Volkan in 2013, and it came back now with all of these natural gradients. So I'm very glad that he's here right now, and I'm telling this this in front of him. Okay, so this work is still kind of ongoing, and we're developing this. So we are kind of showing that by looking into these lambda tilde, you can actually see this kind of classifier, and you can look into different types of data examples like outliers and uncertain and easy. And just by looking at this lambda tilde, you can characterize it. Okay, I'm not going to go into the detail of this, but just show you how it comes out to be. So the kind of things that we do is that we could take some pre-trained deep learning models. So this is on MNIST. I forgot what model it is, but it's something from here. You take that model, you try to extract these lambda tildes, and then essentially easy examples, you see these are the ones where they're very regular examples. There's nothing special about them, but you can characterize outliers by looking into lambda tildes. So essentially these are like, so this is like a 5 that's been mislabeled as 3, 9 that's mislabeled as 3. So you can actually figure this out. You can also figure out different kind of example that the model is kind of confused about. So they're probably labeled fine. So this is 1, but it kind of look weird. This is 3, it looks kind of weird, right? So these kind of things you can get out of the memorable experiences. So this is the kind of thing that we are doing. Well, again, the message is that you choose the posterior approximation. Really, that's the only choice that you need to make. You choose the posterior approximation, you plug it in the Bayesian learning rule, you get these lambda tildes, and they naturally tell you the criteria to categorize these different types of example. And it naturally comes out of it, right? So there are all these concepts like support vectors, influence function, inducing inputs. They're used in very different contexts for different models. And they can now all come together with the same concept of memorable experiences. So this paper is not out yet, but it takes time to write this because it's really, again, a big paper that unifies lots of things. But the main concept I've already told you. So this kind of computation is very cheap because you just take a pre-trained model and just read things off of it. Okay. So this, we are kind of developing the theory of all of these things, and I'm writing another long paper on this, on something that I call base duality. It's an extension of existing duality concepts in optimization, like convex duality and duality in information geometry and other places. And we're very lucky that we have generous funding throughout the years through government agencies. We've got lots of funding, and we have lots of interesting people all across Japan and also around the world who are working on using this base duality to make AI system that learns adaptively, robustly, and continuously. So, okay, I have maybe 2 minutes I'll take, and maybe just hint on the adaptation because we're running out of time. I also want to spend some time on questions. So the last thing is, like, now that we are able to understand what knowledge is important and relevant, can we use it to somehow then freely adapt to the future? So we've been working on a lot on continual learning for the past 3 years or so. And essentially the idea is that first you use this duality to figure out what is relevant, and then we try to freeze them and then not forget them. Okay, so cartoon is like this. If you have first task, you have a classification problem, you learn a classifier, then you identify important examples, maybe they lie next to the boundary, then you freeze them. And then when the next problem comes in, you try to train it such that you don't forget the past. It's a kind of very simple concept, and you kind of repeat this. So this is sort of this continually learning without forgetting. Now, this construction is very simple, but again, this is connected to a bigger principle. And again, it's base duality. And the kind of thing that we actually get here, so we've written this paper, Functional Regularization of Memorable Past, where we show that what people were using before, so people use this weight regularization method. This is from the Kirkpatrick method, the EWC method originally that was proposed. Here you use this kind of weight regularization. And this kind of helps you to balance the old and the new information. So this is the new information, this is the old information. But now we are showing that if you go into this dual of this weight regularization, this is like a Gaussian process. So this is the dual space is in the function space. And when you write down these regularizer using this duality principle, you get very natural kind of regularizers. So here, what actually happens that there's two sets of dual variable because it's a Gaussian, and the one dual variable tells you that the prediction should match. This is written for binary, so sigmoid, and the functions outputs the prediction should match on the old examples, and what you get with the new parameter. But also the more important examples should be weighted appropriately. So the second dual variable modifies the kernel and takes care of the uncertainty. So it's actually very natural, and we've been doing this thing, and this is all connected to Bayesian learning rule. And over the years, you will kind of see papers that will kind of unify all of these things. But what we have shown so far with the work that is out, and I'll encourage you to look into this knowledge adaptation prior, where we're able to show that this kind of regularizer, the form of the regularizer, it has this universal form, meaning like any adaptation method should be using this kind of form. So adaptation in SVMs, adaptation in like knowledge distillation, and like teacher-student framework, that other frameworks that exist in SVM, and those that use in online GP, they're all connected through this kind of mechanism where you're doing this kind of functional regularization. Okay, so I encourage you to look at that paper, and I'm not going to show you this animation, but with this I'll finish the talk. The summary is basically that I showed you a lot of things, but to remember here is that this is a new kind of perspective of Bayes, and it's suited for this kind of modern machine learning. So doing this kind of adaptive and robust deep learning, and we're hoping this will be useful there. And the main idea is really to always see learning algorithms and learning objectives as some kind of approximation of the Bayesian objective, where there's an entropy present there, and you're choosing an approximation, posterior approximation, and by choosing the posterior approximation, you can unify a lot of existing concepts like derived learning algorithms using Bayesian learning rule, or show different kind of duality or robustness criteria that exist, and maybe generalize this kind of ideas of important examples through this memorable experience concept, and then use them for generic adaptation. So no matter what the model is, you can always kind of find this kind of Bayesian side to it. So we're really now working towards this kind of common principle of Bayes duality for AI that learns like human using these principles. So check out these papers. 4 of them are out. 1 is not out yet. And thanks a lot to many collaborators, and it's a picture of the group. So if we have many openings, if you're interested, come and join us.
All right. Thank you, MT. So maybe I can ask a quick question, and then we go over some of the questions. So from what I understand, you don't look at problems directly in the parameter space. You lift the problem into some distribution space, or queue of data. And then the way you wrote things out, and one of the questions mentioned this, you get somehow KL on the right, you end up running something like proximal point on the distribution space. Then you parameterize them with different distributions, and that kind of leads to different algorithms that are also adaptive. So it's interesting. And somehow you also related this to things like stochastic smoothing. Like if you use the Gaussian, you end up getting a variance. I think you fix a variance or something like this. When you fix the variance, then you get to stochastic smoothing. It's an interesting perspective. I think that trying to come up with updates through this particular parameterization on the lifted space, then you can do regret analysis. So I like the connection. So my understanding is correct that you don't you don't want to consider this minimization over L. This could be even non-convex. You consider distributions of over this parameter. So I consider this lifting. We had some works on this also applying to minimax games, because you can actually, so if you think about this problem in terms of Q, that the expectation is just a simple inner product between Q and L. So that's actually a convex problem, in fact, linear, right?
Yes.
The solution to this is in fact the delta, right? So you
it's
have
not a delta, actually, it's a Gibbs distribution. So it's
no, without the entropy,
yeah, without the entropy, there's no.
Yes, so you need the entropy there.
Yes.
Then you get the Gibbs. Yeah, you need the entropy.
That's the reason why we call this Bayes. So this is the reason why E.T. Jaynes was also calling this Bayes. So that's the reason why this word has been chosen.
Because you can have a coefficient in front of the entropy term, then you can get different temperatures on the Gibbs. Okay.
And it's called generalized Bayes. It's related to pack Bayes. It's related to like many things in online learning. So it's so like model misspecification, like in robust optimization. Grunwald has done a lot of work on this, for example, you know. So
okay, now I understand the smoothing perspective as well. Okay, thank you very much. So maybe we can answer some of the questions on the Q&A.
Okay, so I'm just looking at the Q&A and not the chat. Sure, is that okay? Okay.
Yeah, Q&A.
So if doing, so there's a question by Manish, if doing Bayesian inference, should we care about balanced classes in training data? So yeah, you should all, well, so ideally we should somehow have more kind of, you know, learning algorithm. If you did a proper Bayesian thing where your posterior, if you sample from it and you put the expectation, you would expect that the posterior will take care of the uncertainty in the class that has fewer examples. So if you put the expectation back in, I would hope that the situation would be better. But of course, it is a posterior approximation, so it will be better to some extent. So it doesn't solve the problem, but it makes it better. So I hope you see why it would be better, because the expectation in the distribution, the covariance matrix for the classes that have fewer examples, the covariance matrix will be larger. So when you sample from it, the answers will go all over the place. So it will be more smooth. Right? So this is how it will balance the information between kind of like imbalance in the training data. I hope that is clear. Okay. So the next question is by Toshi Teruhoma. I hope I pronounced your name right. Could these algorithms somehow be extended to be helpful for causality analysis? Yes. So I really hope that this somehow, you know, be helpful for causal inference in the end, because the Q distribution that you see here can be seen as an intervention mechanism. So this duality stuff that I talked about, really kind of this picture, this animation that I put in front, where we are going and intervening in different parts. The intervention right now are very simple kind, they're perturbation of the parameters, but you can design additional intervention on top of it. So in reinforcement learning, for example, you can see policy as an additional thing that's being added. And then the uncertainty on the parameter is this distribution thing that's going to somehow affect the policy. So I really expect that this will be useful there. I mean, I'm not an expert at that, so I work on that, but if anybody's interested in doing this, I'm really open to talking about this. There's another question then by Manish about, please give some insights over why good adaptive algorithms must use k-priors. So yeah, so that's a great question, and I wish I had a better kind of easier intuition than what's written here. But essentially, what I've written here is this line. So this regularizer, what we show in the paper is that it can reconstruct the gradient of the past. Okay, so just to show you in the previous slide, this is, you could think of it, so this is like kind of k-prior. And actually, if you take the derivative of this, like you will, derivative of this thing, you'll sort of see that somehow comparing the prediction is a proxy for the gradient on the old data. If you know GLMs quite well, then you would actually already see it. So in generalized linear model, the gradient of the loss is the error times the feature vector. The error is basically prediction of the data using your new model. So you can see this thing as prediction and this thing as the old data. In the paper, we proved that this is actually optimal. So you could actually show that if you increase the number of memorable examples, your gradient will become exact. And I didn't have time to show this here, but its animation sort of shows this here that I hope you can see my screen, something has changed here. But essentially, if you increase the number of memorable examples, the gradient become exact in the limit. So this is why this works. And this principle is universal. It doesn't matter what model you're using, always reconstructing the gradient of the past, then it'll give you good adaptation. And the rate at which it does is also sort of kind of optimal, and these things are discussed in the paper. So I hope you can read that. Okay, so there's a question by Richaro Hataya. Can your continual learning model forget? Yes, absolutely. So this is not perfect, right? So if you see here, it's only using a Gaussian approximation, and it's looking into the dual of the Gaussian approximation. So you can think of it as the quadratic approximation, and then the dual is quadratic approximation for each data example. And this is limited because there might be non-quadratic effects around for some example. So those can lead to forgetting. So we are still kind of thinking about what exactly is needed to take care of this kind of heavy-tailed stuff. It's a very difficult question, actually, in general. Okay, there's a question by Chibin. The gradient of lambda I can indicate how good of samples in your talk. Could you explain more how to infer the good or the bad sample from lambda I? Great question. Sorry, these things are not written down in the papers right now, so I tend to skip these details. But maybe I could show it in this slide. This slide is a little bit better. What exactly actually happens is that what you can show, maybe this figure is the simplest. So here what I'm showing is that there are three kinds of example. This one is easy because it's correctly classified. This one is outlier because it's lying on with the circles. This one is uncertain because it's very close to the decision boundary, right? Now, if you look into the marginals of this global posterior, essentially like the ones that for each loss function, they look like this. So essentially you can overlay them on the logistic loss. So if this is like a logistic loss, like a hinge loss, if you're on this side, you are outlier. If you're on this side, then you're classified correctly. So it's very low loss, so zero loss almost. And if you're at the boundary, you're kind of doing, so what essentially does this perturbation is that we perturb these local marginals. And if you perturb them, then you could see that these guys don't change much. Like because the loss is flat for the green line, they have very little lambda tilde I. So this is kind of the mechanism to study the perturbation. You look into the moments, and it's a Gaussian. There are two moments. Two moments give rise to two measures, and so you have four types of examples. And that's how it's done. Sorry, it's very quick, but I hope in the recording it might be. You can go back and look at that. Happy to also talk about it later to some of you if you want. So email me about that. Okay, so last question here. Is there any paper conducting annealing, I guess you were writing, is there any paper conducting annealing type approach in which you lower the variance such that you find the global minimum with this VLR framework? Yes, great question. I wondered how to quantify the capability of global minimization with this method for the evaluation functions with sharp gradient, which will be smoothed out with large variance. So yes, this is actually, it's an ongoing thing right now, and we haven't shown this, you're right, but I think there's a lot here, and I don't even know where to begin. So I think there is some work on this cold posterior effect that they use, although I don't like the direction that it takes, because it talks about Bayesian versus non-Bayesian. But you're exactly right that if you temper the entropy, it will kind of smooth more, so it will correspond to a different kind of posterior, and maybe something that is more shrink or more. This is actually related to some of these adversarial perturbation methods in deep learning, so like sharpness aware minimization and adversarial weight perturbation, and I forget the name. There's a low pass filtering method, also entropy SGD. So those are the four things that come to my mind. These kind of tempering is being used in these methods. Connection to BLR, people have not made, unfortunately, because this work is still kind of, people are taking time to understand it, but they're very closely connected. So I think the Bayesian principle can help us to understand how to temper things. These tempering parameters are also studied in pack-based literature by Grunwald and others. So there is some theoretical results on this, why this actually improves the generalization. So I would encourage you to check that out. And if you need these references, please send me an email. Okay, I'll do maybe last question.
So maybe we try to go quick and wrap things up.
Yeah. So have you studied privacy of the solution? I haven't, so that's the answer. but yeah, it should be related to differential privacy. So the K-Priors work is definitely related to differential privacy. All right, so I'm done.
All right, thank you, MT, and thanks everybody for joining this edition. The video of this particular session will be on YouTube, I believe, both at RIKEN's channel as well as EPFL CIS channels. You have MT's contact. Feel free to follow up more questions with him. And I think that we hope to have a joint EPFL AIP event both in Switzerland and in Japan. So hopefully we'll get to also talk in person. So thank you, MT. Thank you, everybody. And have a great evening in Japan and have a great afternoon in Lausanne.
Thanks for having me. Thank you.